In this section, we're going to solve more equations, and in the process of solving the equations, we're going to have to use some of the identities that we had from the previous chapter. So I've written over here on the board our reciprocal, ratio, and Pythagorean identities. We also may have to use a double angle formula or a half angle formula, something like that, in the process of solving these equations. So let's go to the board now and look at our first problem. We have square root 2 cosecant theta plus 5 equals 3. I want to solve this for theta. So I'm going to begin by adding negative 3 to both sides. So I have square root 2 cosecant theta plus 2 is equal to 0. Now I guess I shouldn't have done that, but anyways I did. So now I'm going to add negative 2 to both sides and divide by square root 2. I get cosecant theta is equal to negative 2 over square root 2. Now cosecant theta is 1 over sine theta, so here I've used one of my identities. 1 over sine theta is negative 2 over square root 2. So I have these two fractions equal to each other, so what I'm going to do is take the reciprocal of each one and get sine theta is equal to negative square root 2 over 2. So I put a little extra step in here in the beginning trying to put this in standard form, but that isn't what I wanted to do. What I want to do is solve for cosecant theta. Then I write cosecant as 1 over sine. That's one of my identities. So I have these two fractions equal to each other. I can't, what I want to have is a sine theta rather than 1 over sine theta. So I just take the reciprocal of both sides and get this. Now I'll move over here, and square root 2 over 2 tells me that the reference angle for theta is going to be 45 degrees. The negative sign here, the fact that sine theta is negative, tells me that theta is going to be in quadrant number 3 and in quadrant number 4. So I have theta in quadrant 3 and theta in quadrant 4 with a reference angle of 45 degrees. So in quadrant number 3, my solution will be theta equal to 180 plus 45, which will be 225 degrees. And then in quadrant 4, I'll have 360 minus 45, which will be theta equal to 315 degrees. So here's my two solutions between 0 and 360 degrees for theta. So I had to use an identity in the process of solving this. I get sine theta as negative square root 2 over 2. I get my reference angle right here, and then I know from the sign, algebraic sign of this, and the fact that it's a trigonometric sign, that I must be in quadrant 3 or in quadrant 4. So I find two angles in those quadrants for which the reference angle is 45 degrees. Now, let's look at our next problem, problem number 2. Sine 2 theta minus cosine theta is equal to 0. Well, here I have sine of twice an angle, and here I have cosine of just the angle itself. So I have 2 theta here and theta over here. So I'm going to have to do something about that in order to solve this equation. But what I want to do first is take the graphing calculator and maybe graph y equals sine 2x minus cosine x and see where this graph crosses the x-axis between 0 and 360 to get an idea ahead of time of what the solutions are going to look like. So let's go to the graphing calculator now and do that. Well, first of all, let's look at my y variables. Here I have y1 equals sine 2x minus cosine x. Now I'll look in the window here that I have, and you can see I've got x going from about negative 360 to positive 360 in increments of 90, and y is going to go from negative 4 to 4. So let's take a look at the graph of this. So you can see it's winding up to x equals 0, then it crosses 1, 2, 3, 4 times between x equals 0 and y equals 360. Now what I want to do is trace that out. Let's just see. X equals 0, y equals negative 1, so I'm going to start right here. Now let's move the cursor up. There I have a y value of 0 when x is 30 degrees. So 30 degrees looks like one solution to the equation. So I keep going. Next y value at 90, so 90 is another solution. I'll keep going here. And did I go by it? No. 150 degrees is a solution. And keep going to this last one. It looks like it's going to be 270. And let's see, I better back up. Went past it. Yeah, 270 degrees. Okay, so using the graphing calculator then, I found it looks like I'm going to have solutions of 30 degrees. What I wrote them down right here, 90, 90 degrees, 150 degrees, and then that last one was 270 degrees. So what I want to do is see if we can't algebraically and using our trigonometry solve this equation and see if these are the four, and see if we can get these four solutions. So let's take a look. First of all, I have sine 2 theta minus cosine theta is equal to 0. I'm going to use a double angle formula here and write sine 2 theta as 2 sine theta cosine theta, and then I have my minus cosine theta equals 0. That way I've taken my angle 2 theta and written it as trigonometric functions of just theta. In order to solve this equation, I have to have the same angle in each place. Now I'm going to look at, here I have cosine theta common to each term. Let's take that outside. What's left is 2 sine theta minus 1 equals 0. So 2 sine theta minus 1 equals 0. The product of this and this equal to 0. Let's set cosine theta equal to 0, or 2 sine theta minus 1 is 0. Well, if cosine theta is equal to 0, remember the graph of cosine looks like this, where this is 360, this is 180. So the graph crosses at 90 and 270 degrees. So cosine theta equals 0 means that theta is going to be 90 degrees or 270 degrees. So there's two of those solutions I got from the graphing calculator. Now, to solve this for theta, I'm going to first of all add 1 to both sides, then divide by 2. And I'll end up with sine theta is equal to 1/2. So I get a reference angle for theta of 30 degrees. Since sine theta is positive, I know I'm going to be in quadrant 1. And since it's a sine function, I'm also going to be in quadrant 2. So in quadrant 1 and quadrant 2, with a reference angle of 30 degrees in quadrant 1, I get theta equal 30 degrees. In quadrant number 2, I'll get theta equal to 180 degrees minus 30 degrees, which is 150 degrees. So sure enough, here's the four solutions, 90, 270, 30, and 150. Those are the same four solutions that I got by graphing this equation, or y equal sine 2x minus cosine x on the graphing calculator, and then seeing where it crossed the x-axis between 0 and 360. I got four solutions by doing that. I solve it algebraically, and I get the same four solutions. So let's go to our next problem. I have 2 cosine theta plus 1 equals secant theta. I want to solve this for theta. So I'm going to need not only the same angle, which I have, but I want to get the same trigonometric function in both places. So I'm going to rewrite this as 2 cosine theta plus 1 equals, instead of secant, I'm going to write 1 over cosine theta. So I use my reciprocal identity to write secant theta as 1 over cosine theta. Now, to clear this equation of fractions, I'm going to multiply both sides of it by cosine theta. So let's do that next. So I'll multiply this side by cosine theta. And I just have to remember that I can't multiply both sides of an equation by 0. So if I end up with a solution for theta that makes cosine theta 0, I'll have to disregard it. In any case, I multiply here, and I get 2 cosine squared theta. And then I multiply here, and I get cosine theta. And I multiply on this side and just get 1. Well, here I have a quadratic equation again. 2 cosine squared theta plus cosine theta minus 1 is equal to 0. I'll try to solve this by factoring. And what do I have? Let's see. 2 cosine theta and cosine theta. And then let's see, I'll put in 1 and 1. Inside is 1 cosine, outside is 2 cosine. They differ by 1 cosine, and I want to make this 2 cosine positive because this is positive, so I'll make the other one negative. So setting the product of these two things is 0, so setting each of these factors equal to 0, 2 cosine theta minus 1 is 0, or cosine theta plus 1 is equal to 0. I get these two equations to solve right here. They're just linear equations in cosine theta. I'll solve the first one by adding 1 to both sides, dividing by 2. I have cosine theta is equal to positive 1/2. I'll take my second equation and add negative 1 to both sides. Cosine theta is equal to negative 1. This one I can solve very quickly by just remembering what the graph of cosine theta looks like. It looks like this, where that's 360 and that's 180 degrees. So I can see that cosine theta is -1 when theta is equal to 180 degrees. So here I have one solution, 180 degrees. Over here, cosine theta is equal to 1/2. That will give me a reference angle of 60 degrees. Cosine theta is positive in quadrant 1, okay, and also in quadrant 2. Cosine theta is positive in quadrant 1 and quadrant 2, but quadrant 4. Cosine theta is positive in quadrant 1 and quadrant 4. So a reference angle of 60 degrees in quadrant 1, that gives me theta equal 60 degrees. In quadrant 4, that will give me 360 degrees minus 60 degrees. Theta will be equal to 300 degrees in that quadrant. So let's see, I get three solutions. Theta equals 60, theta equal 300, and theta equal 180 degrees. I have to just check and make sure that none of these solutions make cosine theta equal to 0, and they don't because they came from cosine theta equal 1/2 and cosine theta equal -1. So that multiplication property of equality that says you can multiply both sides of an equation by any number you want except the number 0 still holds in trigonometry. So we have to be careful when we multiply both sides of an equation by an expression that contains the variable that we make sure we haven't multiplied both sides by 0. Let's look at our next problem. Square root 3 sine theta minus cosine theta is equal to 1. So I want to solve this for theta, and I have a sine theta here, and I have cosine theta here, and I can't see an identity or a substitution that will get me the same trig function in both places. So a little trick to do in a situation like this is to separate the two trig functions on opposite sides of the equation. So I'm going to write this as square root 3 sine theta equals 1 plus cosine theta. So I've separated my sine theta on one side and my cosine theta on the other. Now, in order to use one of my Pythagorean identities, I need the squares of sines and cosines. So what I'm going to do now is square both sides of the equation. But remember from algebra that occasionally introduces extraneous solutions. So I want to make sure that I'm still going to square both sides of the equation, but I'll have to check my solutions in the end to make sure that I didn't introduce any extraneous ones. So let's square both sides of the equation. Square this side of the equation, I'll get 3 sine squared theta. Square this side of the equation, and now I'm going to have to square this binomial, 1 plus 2 cosine theta plus cosine squared theta. So you don't want to forget that middle term when you square a binomial. It's a plus b squared is a squared plus 2ab plus b squared. Now, it looks like it's mostly in terms of cosine, so I'm going to use a Pythagorean identity right here and write this as 1 minus cosine squared theta. So now I have everything in terms of theta and everything in terms of cosine. So let's multiply this out. 3 minus 3 cosine squared theta equals 1 plus 2 cosine theta plus cosine squared theta. So let's see, I'll add negative cosine squared theta to both sides. 3 minus 4 cosine squared theta equals 1 plus 2 cosine theta. Let's multiply both sides by let's not do that. Let's have 4 cosine squared, or minus 4 cosine squared theta. I'll add negative 2 cosine theta to both sides. Negative 2 cosine theta, and then I'll add negative 1 to both sides and get plus 2 equals 0. So now I'll multiply both sides by negative 1 and get 4 cosine squared theta plus 2 cosine theta minus 2 is equal to 0. Let's see, I should have probably multiplied by negative 1/2 here because I see I have a 2 common to each term. Let's divide both sides by 2 real quickly. 2 cosine squared theta plus cosine theta minus 1 is equal to 0. Okay, so again, we'll factor this. 2 cosine theta and cosine theta, 1 and 1. Inside is 1, outside is 2. I want that to be positive, so I'll do it like this. Positive 2 cosine theta plus a negative 1 cosine theta gives me the same thing that I had in the last problem right here. So these are the same factors I had in the previous problem, so I'm just going to write down my solutions. from the previous problem, theta is equal to 60 degrees, theta is equal to 300 degrees, and theta is equal to 180 degrees. So here are my three solutions, and I have to take these three solutions and check them in the original problem to make sure that I haven't introduced any extraneous solutions to this equation. So first I'll take 60 degrees. The sine of 60 is square root 3 over 2. So I'll have square root 3 times square root 3 over 2, that's 3/2, minus cosine of 60 is going to be 1/2. So 3/2 minus 1/2 is 1. So 60 works. Now let's try 180 degrees right here. Sine of 180 degrees is 0. Cosine of 180 degrees is -1. So I have 0 minus a -1, or 1 equal 1. So that solution works. Now if I try 300 degrees, the sine of 300 degrees, 300 is in quadrant number 3, is in quadrant number 4, so the sine is negative. So I get negative square root 3 over 2 times square root 3 is -3/2. And then the cosine of 300 degrees is 1/2, so I have -3/2 minus 1/2, that's -4/2, that's -2. So I end up with -2 equal 1. That's not a true statement, so I have to disregard this solution. It's an extraneous solution to this equation. So it's okay to square both sides of an equation, and in this case I had to do that so that I could use a Pythagorean identity. But if you do that, you need to check each solution in the original equation to make sure you haven't introduced any extraneous solutions. Let's try a couple more problems here. So cosine x minus cosine 2x equals 0. Okay, I need to get just the same angle x, and here I want solutions for x between 0 and 2 pi. So I'm going to rewrite this using one of my double angle formulas for cosine. So I have cosine x minus, now the double angle formula I'm going to use is the one that says 2 cosine of 2x is 2 cosine squared x minus 1 equals 0. Because I already have a cosine in the formula, so I might as well introduce just the double angle formula that involves only cosine. So I have cosine x minus 2 cosine squared x plus 1, when I remove the parentheses here with the negative sign out in front, equals 0. So -2 cosine squared x plus cosine x plus 1 equals 0. Multiply through by -1 and get 2 cosine squared x minus cosine x minus 1 is equal to 0. Now this is another equation that will factor like the ones that we've had previously, so I'm just going to leave it at this point. The important part of this problem is that you see that we can use a double angle formula here to write this as 2 cosine squared x minus 1. Then I've got a quadratic equation that's simply quadratic in cosine x. So I put it in standard form. The rest is factoring or using the quadratic formula to find solutions. Let's go on and look at our next problem. 4 sine squared plus 4 cosine minus 5 is equal to 0. So I have sine squared x, and here I have cosine x. I need the same trig function in order to write this as a quadratic equation that I can either factor or use the quadratic formula on. So I'm going to use a Pythagorean identity and write sine squared as 1 minus cosine squared plus 4 cosine x minus 5 equals 0. So I have 4 minus 4 cosine squared x plus 4 cosine x minus 5 equals 0. Now let's say I'm going to collect some similar terms here, and I'm also going to multiply through by -1. So when I do that, I get 4 cosine squared x minus 4 cosine x, and then I have 4 plus -5, which is -1. Then I multiply by -1, and so I get +1 equals 0. This is factorable, and it factors into 2 cosine x minus 1 times 2 cosine x minus 1 equals 0. So I have the same factor in both places, so I'll just set that factor equal to 0. 2 cosine x minus 1 equals 0. Cosine x is equal to 1/2. So cosine x is equal to 1/2 by adding 1 to both sides, then dividing both sides by 2. I get my reference angle is, this one I want in radians. I was going to say 60 degrees, but I want this in radians, so I'm going to write here as pi over 3. Pi over 3 radians, and it's a cosine function. It's positive, so I'm in quadrant number 1, and I'm in quadrant number 4. So in quadrant number 1, x is equal to pi over 3. In quadrant number 4, My reference angle is pi over 3. So this is 3 pi over 3. All the way around is 2 pi, which is 6 pi over 3, minus pi over 3 is going to be 5 pi over 3 for x. So in quadrant number 4, x is equal to 5 pi over 3. So two solutions, x equal pi over 3, x equal 5 pi over 3 for my radian solutions between 0 and 2 pi. So in any case, there's a look at some equations that we can solve where we also have to use some of the identities that we developed in the previous chapter.